All right, let's talk about high-performance computing, or HPC. We're going to peel back the curtain on what makes a supercomputer so, well, super. And here's the cool part. The very same ideas that power these massive machines are probably working inside your laptop right now, and they are absolutely critical for training the huge AI models we see everywhere today. So let's break it down.
So just to get a sense of the scale we're talking about, let's start here. Your laptop, a pretty powerful machine, probably has something like 8 cores. Think of those as 8 little workers. Now, a modern supercomputer, it can have over 1 million. That's not a small team anymore. That's the entire population of a city, all focused on solving one single problem. So how in the world do you coordinate all of that?
Well, the secret isn't trying to build one single, impossibly fast brain. That's not how it works. The real magic, the secret sauce, is something called parallelism. It's all about getting all of those millions of processors to work together at the exact same time on tiny little pieces of a giant problem. It is teamwork on an absolutely mind-boggling scale. So let's look at how that teamwork is actually organized.
First, let's start small. Let's look at the parallelism that's happening right inside your own computer. This approach is often called the shared whiteboard model, and it's the perfect place to start our journey.
This first method is officially known as shared memory programming. The idea is actually pretty straightforward. All the processors, or what we often call threads in this context, they're all inside one machine, and they can all see and access the exact same pool of memory. Programmers use tools, a common one is called OpenMP, to help manage all this.
And this whiteboard analogy is just perfect for understanding it. Picture this. All your computer's cores are workers, and they're all in the same room. The computer's memory, that's the giant shared whiteboard in the middle of the room. Anyone can walk up to it, read it, and write on it. But, and this is the really critical part, they have to coordinate. They have to synchronize so they aren't all trying to write in the same spot at the same time and erasing each other's work. It's a system built on total cooperation in a shared space.
Now, the huge advantage here is that it's incredibly fast and efficient. Sharing information is as simple as just looking up at the whiteboard. But there's a big downside. You are fundamentally limited by the size of that one room, by the power of that one single machine.
Which, of course, leads us to the really big question. What do you do when your problem, maybe you're simulating an entire galaxy or training a massive AI model? What do you do when it's just too big for one computer, no matter how powerful that one computer is?
Well, to solve that, we need a completely different way of thinking. This is where the separate offices model comes into play, and it's designed specifically for coordinating work across tons and tons of different computers.
This is called the message passing model. Now, in this world, every single processor is totally independent. It has its own private memory, its own little notebook. They can't just look over and see what the other person is doing. To cooperate, they have to package up information and explicitly send it as a message to a specific coworker. The tool everyone uses for this is called MPI, which stands for Message Passing Interface.
And this analogy just nails the difference. So instead of one room with one whiteboard, I want you to imagine thousands of workers, but each one is in their own private office. Each office is a separate computer, which we call a node. Now, if they want to share an update, they can't just yell across the room. No, they have to write a letter, address it, and send it. It's a bit more work, sure, but it means you can scale your operation across thousands of buildings. This right here, this is the core idea that makes supercomputing possible.
So problem solved, right? We just keep adding more and more processors, and our programs get faster and faster forever. Well, not so fast. It turns out there's a catch. There's a fundamental speed limit to all of this.
And that limit is defined by something called Amdahl's law, from the computer scientist Gene Amdahl. Now that sounds a little dense, but what it's really saying is this. Your total speedup will always be held back by the parts of your code that absolutely cannot be run in parallel, the stuff that has to run one step at a time on a single worker.
This chart makes it crystal clear. So imagine 90% of your code is awesome. You can split it up across thousands of workers. Great, but that last 10%? That has to run solo, in a single file line. No matter how many thousands of processors you throw at that parallel part, you'll always have to sit and wait for that 10% serial part to finish its job. That tiny little slice becomes your ultimate bottleneck.
So the real takeaway is this. Getting massive performance isn't just about adding more hardware. It's about being really clever in how you write your code to shrink that serial part down to be as small as humanly possible.
Okay, so all this theory is great, but where does it actually show up in the real world? Well, these two ideas, The shared whiteboard and the separate offices are the absolute bedrock of modern artificial intelligence. They are the hidden engine behind the AI tools that you and I use every single day. Let's see how.
This table really ties it all together beautifully. That whiteboard model, the shared memory idea, is used inside a single machine's CPUs to get massive datasets prepped and loaded incredibly fast. Its job is to make sure the super powerful GPUs are never just sitting around waiting for data. And then the separate offices model, that message passing idea, is used to coordinate the training process across hundreds or even thousands of those machines, keeping the AI model's updates perfectly synchronized.
And in the AI world, they've got specific names for these strategies. When you split a huge data set across a bunch of chips, that's called data parallelism. But sometimes the AI model itself is too big for one chip, so you have to split the model up. That's model parallelism. Both of those rely on that separate office's message passing to work. And it doesn't even stop there. Once the model's trained, the shared whiteboard approach is used for something called inference, which is just a fancy word for making the model run really, really fast to give you a quick answer.
So you see, it doesn't matter if you're forecasting a hurricane or you're powering the AI assistant on your phone, the fundamental challenge deep down is exactly the same. It all comes down to intelligently managing parallel work, knowing when to use the shared whiteboard and when you need the separate offices.
And that leaves us with a really interesting final thought. As the problems we want to solve just keep getting bigger and more complex, is our main bottleneck building faster hardware? Or is the real frontier our ability to write smarter, more efficient, parallel software that can truly unlock the incredible power of the machines we already have? That's the central question driving the future of computing. Thanks so much for joining me.